It's okay so far. So let's just keep it this way. Give me a second. Okay. Any other questions, comments? So let's start before I get disconnected. So, sorry, share the screen. Oh, okay. Now I can't share the screen. Only the host can share the screen, which is very interesting. So let's I'm gonna disconnect. So I'm gonna end. Maybe you can end the meeting. Who can end the meeting? So let's see. Sorry, let me see if I can declare myself host here. This is very weird. Let me. Right, I'm connected through my computer and also my iPad. On my iPad, I'm not the host, so I can't share. So let me disconnect from my iPad and come back. Just give me a second. See if this works. Okay, I think it works now. It should work. Okay. Remove my. Okay, this is better now. Start. Okay. Okay. So now you can see my screen, right? Can you see my screen? Screen now. Okay, good. Okay, so let's begin. So we started talking about linear regression, and in particular, would like to talk about high-dimensional sparse regression. And this is basically the main example, or the first example that we're going to do of high-dimensional statistic. And it's a very, I would say, important example, and also useful in practice. So recall that the linear regression problem is something like this. I have observations, and these observations are written as a function of some covariate, or something called independent variable xi, plus some noise, wi. And here we are assuming that this function is linear in its argument, and the argument is a d-dimensional vector, so a linear function in this case would be something similar to what I have written here. So it's an inner product of theta star times xi, sometimes called a linear functional. So you map a vector to a number, and that's what you get. You get a linear function. And so theta star is also d-dimensional. And this is the parameter of interest. And we have a sample size n. And you can rearrange things in this form. So you can write, if you, what I'm doing here. So if you write down y to be, you can write down y as, so this would be y1, y2, yn. So that's the y vector. And this is equal to x, which is the design matrix. This is x times theta star. And if you consider each row of capital X as x1 transpose, x2 transpose, and so on, you can see that this just translates to the product here. So x1 transpose times theta star equals x1 transpose theta, and so on. And so these are alternative ways of writing it. And the so the assumption is that the number of covariance D is much bigger than n. So this matrix, design matrix, is a fat matrix. So fat matrix as opposed to a tall matrix. And this also means that the kernel of X is non-empty. So the kernel is the set of vectors that are mapped to 0. So this is, the kernel is always non-empty, but this is non-trivial. So the kernel is bigger than the trivial kernel, which just contains the 0 vector. So for any u which is non-zero in the in the kernel, if I add that to the theta, so if I pick u in the kernel, and then if u is non-zero, which is allowed because the kernel is non-trivial in this case, and if I add it to the theta star, then x times theta star plus u is equal to x times theta star. And so this means that I can replace theta star with theta star plus u, and the distribution of y does not change. So this tells us that theta star itself is not identifiable. So we can't try to estimate theta star. Okay. So let me see if I can. So any questions so far from the recap of the previous lecture? Okay, people seem to be okay with this. Okay, so now what we can do here is we can put some more assumptions on theta. I can try to add an assumption on theta such that it makes it identifiable, and the usual assumption in high dimensional statistics, it has been and is still quite relevant, is this assumption of sparsity. And that's the I have written something on this slide. I think it's not there. Okay, so the sparsity, what does the sparsity mean? The sparsity means so sparsity means most elements of theta star are 0 or small, let's say, slash irrelevant.
Pearson has one remaining.
Sorry? Was that a question? Was that some background noise? Okay, let me know if you have any questions. So the right, so the basic, for example, the simplest form of sparsity assumption is assuming that theta star has many zeros. And so to formally define it, consider defining this support. So support of theta star is the set of indices, this guy, the set of indices such that theta star, the set of indices j such that theta star j is non-zero. Okay, so basically, very simple example. Suppose theta star is 0, 1, 2, 0, 0, 5. Then the support of theta star is just 1, 2 is not there, 3 is not there, 4, and 5. So these are the indices of these elements. Okay. And so I can basically count, and the size of the support counts how many zeros there are. Sorry, the opposite. This is the opposite of this is the support. So again, so let's say 0, 1, 2, 0, 0, 5. So then the support would be 2, 3. So 1, 2, 3, 4, 5, 6. So the non-zero part, the indices of the non-zero elements. Okay. And the size of the support, or S theta star, let's say, the size of this guy is, in this case, 3 is the number of non-zero elements, and this is sometimes called the L0 norm. And you can assume, for example, that this size is S, and S is much less than D, the dimension of the vector. Okay, so in this case, this is not much less than, so this is in R to the 5. So D here would be 6. D is 6 and S is 3. It is moderately sparse. But you'd assume that this S, the number of non-zero elements, is much less than S. This is sometimes called hard sparsity or L0 sparsity. And this is sometimes referred to as you can see here, L0 norm. The number of non-zero entries. It's not a proper norm. You can drive it as a limit of these other things, which are the LQ norms, and those are proper norms, and those allow you to define more lenient versions or weaker versions of sparsity. So and a weaker notion is this, so weaker sparsity assumption. You can assume that theta belongs to the LQ norm ball of a certain radius. So the LQ norms are defined like this: I from 1 to D, J from 1 to D, theta J to the Q, and then 1 to the Q. So these are going to be norms if Q is bigger than or equal to 1. So norm if Q is bigger than or equal to 1, but we still can work with, let's say this guy has interesting properties, even if, so for example, satisfies the triangle inequality, I believe, even if, to work with this, and even if Q is less than 1. And I shouldn't call them norms. So if I'm calling them norms, it's just for convenience. So what we care is these LQ balls when Q is between 0 and 1. And I'll show you the picture shortly. But you would assume that theta belongs to this sort of LQ ball with a certain radius. Okay, this is just saying that the theta Q to the power Q is less than or equal to RQ. Okay.
Oh, I have one question.
Yeah.
I didn't get it. Why don't you take Q to be bigger than 1 here in the weaker sparsity assumption? Why?
I'm going to tell you. Yes.
Okay.
Yes. Usually that's what people assume is Q between 0 and 1. So the one case of interest, which is Q is equal to 1, this should be 1, is the L1 ball, and that we'll see again. And then there's you can think of the case where Q is equal to 0. If you put 0 here, if theta is non-zero, then something non-zero raised to the power 0 is going to be 1. And if it's 0, if you define 0 to the 0 to be 0, then this definition sort of also works for Q equals 0. It will be equivalent to just counting the number of non-zero elements. Okay, so why do we work with the case Q between 0 to 1? So these are the balls. So let's say if I set so these are the images of these. Sometimes you could write it this way. So these are the images of the unit balls of these sort of norms. They have a name, I forgot, quasi-norm or something like that. J equal to 1 to D, theta J to the Q, less than or equal to 1. So I can plot this for different Qs. So this is Q equal to 1. This is Q equal to, I believe, 1/2. Or sorry, this is like 3 over 4, 3 over 4. And this is Q 1/2. Okay, and so you can see it gets spikier as you decrease Q. And so if something is within this, let's say Q equal to 2 ball, you can see that it has to be very close. Generally, it has to be close to these axes. So most of the elements are going to be small, right? Whereas here, it still can be more in the, let's say, uniform position that all the elements are equal. So here, if all the elements are equal, the elements have to be very small. Whereas, so this is like this point is 1, for example, 0, 0. This is 0, 1, 0, and so on. Okay, and this point, for example, in the middle is, it has to be small. So if all the elements are equal, you have to be quite small to for the sum to be equal to less than 1. Okay, so it forces you to be sparse.
I see. Okay, so I see. So if Q is bigger than 1, then it does not induce sparsity, but if Q is less than 1, it induces sparsity.
Yes, it forces you to be closer to the coordinate, basically the hyperplane.
I see. Okay, good. Okay, thank you.
Okay, good. No problem. Okay, yeah, so just geometrically, you can play with this and convince yourself that these are interesting sort of cases. But it makes it problematic because which one of these guys is a convex set? Anyone can comment on that.
Q equal to 1?
Yes, so among them, this one is convex. The only one that's convex. These are not convex.
Yeah, that is another issue, right? Yeah.
Yes, it's going to be another issue if you want to optimize over them. But you can see they enforce sparsity more strongly, right? So if you're forced to be in this ball, then you're guaranteed to be more sparse in a sense than if you're guaranteed to be in L1 ball. Right, but that's a different issue. So optimization is a different issue. We're not going to worry too much about optimizing over these balls. We are rather in this course going to work with this as an assumption on theta star. We'll estimate theta in a different way. But people in the statistics work with these type of penalties as well, if you want to add a penalty, but we'll see. Okay, questions so far? Okay, yeah, also Zach said L1 only, yes, so that's correct. No questions? I'll pause a little bit. All good? Okay, so let's move on then. So the first thing that I want to talk about is, so classically, this problem, sparse, let's say linear regression, has been studied in the noiseless case. So in the case where you don't have this noise. So it has been studied in the context that you have a linear system. Basically, this would be a linear system then. And you know that the theta star there is a theta star that satisfies this system. So you observe y and x. You basically want to solve this linear system for theta star. But as you can sort of, again, imagine, or as we've discussed, because the n is much smaller than d, the system is underdetermined. So it has many solutions. And so you want to find a unique solution which is sparse. And this has been studied, like historically studied more or earlier, and I would say in a different context. And then later people studied at least theoretical results, I would say. Practically, they were sort of proposed, the solutions proposed at the same time, more or less. But the study of this noiseless problems was initiated first. Okay, so let's try to understand this, and then we'll come back to the noisy case. So in the noiseless case, again, you have this underdetermined system, and you want to find a sparse solution. You want basically something that has small L0 norm. And so we can frame the problem as a natural optimization problem. Minimize the L0 norm subject to theta satisfying this system equation. So if you have seen, for example, like numerical linear algebra, if you have an underdetermined or underdetermined system, one way to find a good solution is to try to, for example, minimize the L2 norm. That would be that would give you a unique solution which has some nice properties. So here we're gonna follow the same path, but instead we are gonna minimize the L0 norm. But the issue is that L0 norm is highly non-convex, and it would in fact be a combinatorial problem. So you in order to solve it, you would assume that, for example, the L0 norm theta is k, and that means that there are k non-zero elements. And then you go and search over all possible. So you would have. So how many vectors in RD? I can't say that. So you'd have a d-dimensional vector, and you know k of the elements are non-zero. So you'd want to pick a subset of size k, and there are d choose k subsets of size k from 1 to d. So these are candidate supports for your vector. So assuming k is less than or equal to n, once you choose the support, then the problem becomes solving y equal, I'm going to write it at x sub s times theta s. Okay, x sub s means I'm just picking these s columns, so the columns that are indexed by s. Okay, and then I should probably do it somewhere else. So if you fix the support, the problem becomes simple. Let's do it somewhere else. Delete. So add a page here. So what I can do is, let's say, pick subset S, subset of 1 to D, and then I'm going to look at the problem, which is this is my X, and this is my theta star. So I'm going to go pick this subset S here, and the corresponding subset is here. And so my problem becomes, this is going to be X sub S. This is going to be theta sub S. And then you can see that X times X times theta star would be just XS times theta star S. And so this is equal to Y. And then I can solve for theta star S. Okay, assuming that S is less than or equal to n, this is n dimensional, and XS is full rank, then the solution, so the system has a solution. Okay. So you go and basically you have to try, sorry, it might not have a solution, sorry. Sorry, let me see. This is not necessarily correct. It's going to have a unique solution if it has a solution at all, but I'm not gonna say this stuff right. So
Why
you
not?
tried it.
Why not? I mean, it
Because
is linearly independent columns. So
right, but the question is whether y can be written as a linear combination of those columns or not. So y might not be a linear combination of the columns of xs. If it is, then you can
okay,
solve it,
okay,
right?
okay. Yes.
Right. So you go and pick s and then try to solve this. And let's say the procedure would be something like this. So I'm gonna say fix s of a certain size. So start from size. Start from size s equal to, let's say, n, because then I can solve the system. For s equal to n, if x sub s is, if basically if x is full rank, then there is a subset of columns that's full rank and it's invertible. So in that case, you can, so there's a solution. There is a solution for some s. If x is full rank, and then you drop, so you search over all the s's such that this is n minus 1 and see if you can find a solution there. If you can, then you drop it again and see until you can, like, you reach a point where you can't, and that would be your, right? So you try to find a subset which is of a certain size, and the system has a solution. If you can find something like that, then it means that the sparse solution at least is that a sparse, and then you can reduce the size of S, search among all the subsets that are smaller, and so on. Okay, does that make sense? Until you can't do it anymore. So at a certain point, then there is no solution of that level of sparsity. It means that the previous solution that you had is the sparsest. Okay. So in general, you shouldn't be like, for example, if this is like just one column, let's say S is equal to 1, y might not be in the direction of any of the columns of x. So there might not be a sparse solution. Then you'd go, you can start from this way. It might be better to do it this way, actually. I'm not seeing that. Start from a smaller one. So try 1, 2. Yeah, this way is going to be much tougher, if anything. But you start from all the subsets of size 1, then all subsets of size 2, and so on. So let's say if there is a solution of size 5, then you might get it. The first time you get a solution, then that would be. Does that make sense? But this is combinatorial. You have to search and choose. Basically, it would be the sum of n choose 1, n choose 2, n choose up to n choose k, where k is a feasible solution. The support of the feasible solution. Any question?
One thing I don't understand, probably I didn't get what you're saying, but you are given the support set, right? The set S, right? And you are given that y is equal to x sub s times theta star s, right?
Yes. We don't know if it's like, we hope so, right? I'm trying to see.
But that's what you're saying, that you are given that support of theta star is s. And
no, okay, so you're right. This is not, I shouldn't say that. This is true. What I'm saying is, I should say, yeah. So theta star is fine. So because this is true, then the other one, yeah, this is true. But what I'm trying.
And then because if x
I'm
has
saying is
linearly independent columns, you can find theta star s.
No, so what I'm saying is that we need to solve something like this. So I don't know if this system has a solution. With that particular theta star that I constructed, why it's always going to have. I mean, this equation is true, then this equation is also true for any s. What I'm saying is that pick s. This, you can call this u if you want. Right? You want to see whether that has a solution.
Uh,
Can you see what I mean?
I mean, I'm still a bit confused. So the problem statement is you are given y and you are given x. So, and you want to find a theta star from minimum norm as L0 norm such that y is equal to x theta star.
No, I'm not trying to find theta. So let's say this is, I'm trying to find theta, but okay, so let me try. What I'm saying is that you're given, delete this, sorry. Given y, which is equal to x theta star, okay, construct the sparsest theta such that x theta is equal to y. I want to find theta. I don't know theta star, right?
Yes.
So if I pick, delete this one as well. Pick a support S and C if x sub s times u equal y has a solution. So this may not have a solution.
Yes, for an arbitrary s, yes.
Right. So you start from small s, so s is of size 1, and you try them all. And if there's one of them that has a solution, this system has a solution, then you have found the one sparse solution, and you're done. Okay.
Yes.
So there.
Yes.
If not, then you'd go to all the subsets of size 2 and try to solve these systems x sub s u equal y for all of them.
Yeah, that is hard. Yeah. Yeah.
Okay. Okay. Sounds good then. Any other questions? Okay, so that's how you do it, but in practice, that's going to be combinatorial hard. In some cases, it works, and you might be actually interested in doing that. Okay, so there is another popular approach which relaxes this L0 norm to L1 norm. So instead of the L0 norm, we try to minimize the L1 norm, and the L1 norm is the closest of these guys to convexity. So it's convex, and so if I do this, if you've taken an optimization course, you might recognize that this becomes a convex optimization problem. Minimizing a convex function subject to a convex constraint, in this case a linear constraint, is a convex problem. And it's an easy convex problem. Not all convex problems are easy to solve, but this is quite easy to solve, and in fact can be written as a linear program, which you can, there's a hint there in the footnote, you can verify this for yourself. And so global solutions of this can be found very efficiently, and for this reason, convex optimization is attractive. So you don't have to worry about whether your algorithm converges to a local minimum, or whether there is a certain algorithm that you have to sort of fine-tune to find the possibly global solution, which often is not possible in practice. You just don't worry about optimization, like the numerical aspect of optimization. You can assume that in practice you can get a global solution or all the global solutions rather efficiently. And so then in theory, you can just analyze the global solutions of this problem and see if they have the right properties. Okay, so that's one of the main advantages of convex optimization, both in practice and from a theoretical perspective. Okay, does that make sense? Questions? See if I can find my.
I have a question about basis pursuit.
Yes.
I don't know how much you want to talk about this, but I took a stats programming class a few quarters ago, and I think the way we did basis pursuit was we projected onto each column and saw which one fit the data best, and then took the residual of that projection and then projected that onto each remaining column. And so we kind of just added one. But
I don't think that's the pursuit. That's projection pursuit, I guess. That's something else.
That's what I was curious about. Is I remember he said something like sometimes this is the way you do it, sometimes this is. There were like a couple things that were right and wrong, but he said this isn't really the class to talk about it. And I guess I'm wondering if maybe this is the class.
So I think that's related to something called projection pursuit, what you described. And then it's more classical and also matching pursuit. So unfortunately, I can't share. So let me see if probably can. Let me unshare my screen, see if I can do it. Probably can share it here, but I need to. Sorry. Open the. Let me try to see if I can. Projection. It's actually a good exercise. So this basis pursuit is, the name is coming from similar, because traditionally in let me reshare back my screen. See if you see this. Okay. So there's a type of statistical technique which involves, oh, you still can't see. Oh, yeah. The most interesting possible projections is one-dimensional dick. So as each projection is found, the data are reduced by removing the component along that projection, and then the process is repeated to find new projections. This is the pursuit aspect that motivated the technique known as matching pursuit. And they're orthogonal matching. So they are related, but this is not this problem. Okay, so they're related to this is a greedy approach, and it may not find the L0 solution or the L1 solution. There is a relation between them, but this was this more traditional problem, and the basis pursuit, the name is derived similar to this. So it's a technique which is like a as an improvement. It was supposed to be improvement on these things: projection pursuit and matching pursuit. So basis pursuit is the L1 penalized version that I mentioned, and you can solve it in this greedy fashion. You can solve it exactly, but it would be interesting to maybe. I'm not sure if I can submit. So there are things which are related. So finding projections of the data that are interesting. But this is. I'll try to see if I can come up with a more problem that tells you the differences. But you probably are thinking about this. Is this what you?
Yeah, this sounds.
Thinking about?
This seems like what we talked about. We did a.
Right. It seems like you were talking about the. Right. It seems like you were talking about the projection pursuit, which is different than. So the basis pursuit is like the naming is also not quite obvious, but right. The basis this is what I think people call the basis pursuit. So this problem, however you want to solve it. Okay.
If you don't have to satisfy the constraint y equals x theta exactly, then and you instead make that like an objective, then it's the lasso problem. Is that also? Yes,
that's what I'm going to talk about next. Yes. So this is in the noisy case, in the noiseless case, and if you make that constraint into an objective, that would be exactly lasso if you do it with a quadratic loss.
So
right.
I have one question here.
Yes.
So your objective is to solve the minimization of L0 norm, and you are relaxing it to L1 norm. But then how do you say that solving one will solve the other one? because
That's one,
it will give
right.
some approximation and something.
That's a great question. I'm gonna answer that question in the next couple of slides. Okay.
Okay. Thank you. Okay.
Yes. That's one of the things that people have tried to answer, and this was more or less solved like in 2004 or something. So in a couple of papers by Donahoe, and then many other people followed, like Candace and Tao, and the whole field. So it's related to this thing called compressed sensing. So this started the whole field of compressed sensing. And this problem, the noiseless case, is the basic problem that sort of compressed sensing is all about. So exactly going to talk about that aspect. What is the relation between the solution of the L01 and the L1 problem? Let's see, I can't see the chat. Okay, so let's talk about that then. So in order to give a more or less complete answer to that question, let's look at this. So what I want to show is that, or want to investigate in what cases, under what condition on X and probably Y, or theta star, do we recover the solution of the L0 problem by solving the L1 problem, the L1 normalization problem. Okay, to do that, we define this notion called restricted null space property. So consider this set in RD, which is defined as a set of all vectors. So this delta is a vector in RD. And I'm using the subscript notation to denote. So this is delta. I'm writing it as delta sub S. So S may not be, so S is a candidate support, let's say, is a set, and S complement is its complement. Okay, so for example, I'm gonna write it like this. So this is delta sub S is just the vector that contains the indices of delta on. So the elements of delta indexed by S and delta sub S complement contains the elements of delta indexed by S complement. And they need not be consecutive, but I'm going to use this. So for example, D could be 5, S could be 1, 3, 5, and S complement could be 2 and 4. Okay, so delta sub S would be delta 1, delta 3, delta 5, and delta S complement would be delta 2, delta 4. And then I can put them together, I get the delta. I usually write things like this. Without loss of generality, you can permute the elements such that they are in a consecutive, close to each other. So they form a consecutive block. It's easier to write things like this. Okay, so I partition delta into these two pieces, and then I look at the L1 norm of each piece. So this is the L1 norm of this piece, and the other thing is the L1 norm of the other piece. And so general idea is that this S is going to be the candidate support is going to be small. So it's more like, the picture is more like this. So I have like, this is delta S and this is delta S complement. Okay, so this is much smaller and this other one is much bigger. And so I want the L1 norm of the big part to be less than or equal to the L1 norm of the small part. Okay, which is quite a strong condition. So this set contains all these deltas, and it has some nice properties, and in particular, it's a convex set, and it's also a cone, actually. So it's a convex. It's actually not convex, sorry, it's not convex. But it's a cone. It is, so anyone knows what a cone is? Mathematically or geometrically? Hello? So for example, in R, like L2, so R2,
It's like ordered.
sorry?
It's ordered pairs x comma t, where the norm of x is less than or equal to t. It's like in a dimension 1 higher than x is the cone. That's how we define them in Vandenberg's classes.
Can you say that again?
It's like in the electrical engineering classes I've taken, we've defined cones as ordered pairs of like x comma t, such that the norm of x is less than
Oh,
in
so
some.
that's a particular cone. That's like an ice cream called ice cream cone. That's a particular cone. So the cone property, yeah, that's an example of a cone. But the cone property is that if x is, let's say if delta is in CS, then t times delta is also in CS for any t non-negative. Okay, so if I scale it by a positive scalar, I'm going to still be in that set. These things are called cones. Yeah, the thing that you mentioned is an interesting cone, but it's a particular example. So in R2, let's say S is equal to, for example, 1. S complement would be 2. So this set would be C1 equals the set of all delta in R2 such that delta 2 is bounded by delta 1. Okay, and if you plot it, it would be something like this. This is delta 1, this is delta 2. Delta 1 is bigger, so it would be, I believe it would be this one, right? So you can see, like, if I rescale things, basically, if a vector is in here, all the direction to infinity is going to be here as well. Okay, those are the cones. Or it could be the other way around. So for example, I could have CF2. Usually you look at things that way, geometrically. So delta 1 is less than or equal to delta 2. That would look like the other way around, which is a little bit better aesthetically. So that's the other thing. Okay, so this is that set. Geometrically, it has some nice features. So the theorem says that the following two statements are equivalent. So for any, so this is a statement that I'm going to mention, and the next statement are equivalent. If I have for any theta star with support in S, the basis pursued has a unique solution equals to theta star. That's one statement. And that the restricted null space property holds in the sense that the null space, this is the null space of X, the intersection of the null space with this cone is the trivial set. So both sets contain 0, and it is saying that nothing but 0 is in the intersection. So for example, if this condition holds, then for any theta star with support in S, if I solve this with y being equal to x theta star, I get back theta star uniquely. Okay, and if I have this property that if I solve this system for y equal x theta star with support in S, and I get back theta star uniquely, then that condition has to hold. I'll let you take a look at this a little bit more. The condition is like the first statement is a little bit more stronger than saying that the problem has unique solutions for a particular theta star. It is saying that the system has a unique solution for any theta star with support in S. And the theorem says that that statement is equivalent to 3. Okay. maybe take a look at this a little bit, see if it makes sense to people.
When you say it has the unique solution theta hat equals theta star, I think this is what you just said, but I just want to confirm. You mean it has the unique solution theta hat among thetas with support in S? Is that right?
No, what I'm saying is, if you solve this, so minimize theta 1 subject to x theta equal x theta star. So this problem has a unique solution. And that unique solution is theta star.
This is like really different from the setting we usually are, or that we're often thinking about though, right? With a really wide matrix.
Why is it a... So this is what you want. So you want to say that if I solve this problem, right, the minimizer is unique, and it's actually the theta star. That's what it's saying.
I'm sorry, I was confused.
Right? Does that make sense? So what the S is here, the support of theta star. But as a consequence, because the solution of the problem is also going to be theta star, so the support of the solution is going to be S as well. But the statement is saying more. So it's just not saying that if I solve this problem restricted to thetas that have support S. So the support comes out for free. So you just solve this problem, convex problem, without knowing anything about the support of S. You just minimize the L1 norm, subject to theta satisfying this linear set of constraints. And the result is saying that if that restricted null space property holds, then your solution is going to be unique and it's going to be exactly theta star. So it's going to have the same support as theta star. But this condition has to hold for S, which is the support of the true theta star. Does that make sense? Let me know if it doesn't make sense. I can try to reword it. What were you thinking about in terms of, you said we usually think differently.
Sorry, I was confused. Instead of that program, I was just thinking of solving x theta equals x theta star.
Right, so that would have many solutions. Right. What we're trying to do is try to find a solution which has minimum L1 norm. So this is saying that you can't have two solutions of the system that have the same L1 norm, and that's the smallest possible. If that's the case, then there's something which has a smaller norm, and there's no other thing that has that norm. So maybe in the proof, I forgot if there's like a picture. Maybe you'll see it in the proof why the solution would be unique. But think about this. This is exactly what you want. Okay. Other questions? Okay, so let's see the proof. Maybe it becomes a little more clear. So the proof is an interesting geometric proof, basically. So consider the so-called... Go ahead.
Yes, I have one question. So you are saying, are you saying that any theta such that x theta is equal to x theta star and that has minimum L1 norm, then theta has to be the same as theta star?
Yes, I'm not saying any... Yeah, basically it says there's just one theta that satisfies this system and has the minimum L1 norm. So among all the thetas that satisfy the system, there is one that has the smallest, and that one is theta star.
To say that you need to have some restrictions on x, right? Otherwise, that probably
that's condition 3. That's the exact condition. So that's the restriction on x.
Oh, okay.
This is the condition that you need. I'm not saying it's going to be always like that. So this statement is saying that the statement is equivalent to that condition.
I see. Okay.
Okay. Other questions? Okay, so let's see if we can prove this. So the proof is interesting. So first we need this notion of tangent, cone, and descent directions. So so the tangent cone to the L1 ball at point or at theta star is defined with this statement. So what this is saying is that the set of deltas such that this tangent cone is a set of deltas that satisfy this condition, and any particular delta that satisfies this condition is called the descent direction for L1 at point theta 0. So why this is called a descent direction? Because this condition is saying that if I stay at theta star, so I'm starting at theta star, and if I look at the direction delta, then there exists, this delta could be big example delta, then there exists some t such that if I rescale this delta to be small enough, so this would be t delta t, and then I add them here, then at this point the L1 norm is less than or equal to the L1 norm of the one that I started. So I can descend on the L1 as a function if I move in this direction for sufficiently a small t, right? So these are descent directions for this function. So generally, a descent direction for a function is something like this. You can just replace it here. So this is saying at theta star, if I start at theta star and move a little bit in the direction of delta, then I can make the function go down, or at least that doesn't go up. Okay. Does that make sense? So why these are interesting? Because if I, for example, start at theta star, and theta star is the true theta, and if I can find the direction which I can descend on L1, and that direction is in the kernel of X, then I can find a solution. I arrive at a solution of the system which has a smaller L1 norm. Does that make sense? So if you take any theta and look at theta minus theta star, this direction is going to be feasible if this direction is in the kernel of X. Okay, so if theta minus theta star is in the kernel of X, then theta satisfies the linear system. So what I'm saying is that delta belongs to the kernel of X if and only if theta satisfies x theta equal x theta star. That's the system we want. So the directions that we want to look at are the directions that are in the kernel. I'm going to call these the feasible directions. So these are directions that are feasible for the problem. And so there exists a minimizer other than theta star if and only if this cone, these directions that are in the tangent cone, these descent directions, that set intersects with the kernel. So there exists a feasible direction which is also a descent direction. Then I can move in that direction a little bit, and I can decrease, or at least do not increase the L1 norm, and so I have at least something as good as theta star, or even better in terms of the L1 norm, and so that violates the uniqueness that we mentioned. Okay, does that make sense? So the condition, this first condition, that there exists a unique solution to that L1 minimization problem, which is equal to theta star, is equivalent to that intersection being empty, okay? Or the opposite of it is equivalent to what I have written here. So that statement fails if and only if this intersection is not empty, non-trivial, which means that it has something other than 0. Is 4 clear to people? Maybe in the chat you can say something. Yes, makes sense. Okay, good. Let me know if it doesn't make sense. Okay, so now what can I do? I can try to, so this statement actually not equivalent because the first statement is saying that this should hold for any theta star supported in S, okay? Whereas the statement that I have there is for a particular theta star. So I can fix this by just taking the union over all theta stars whose support is in S. So instead of looking at the tangent cone at S theta star, I look at the union of all these tangent cones at theta stars whose support is in S. So these are the theta stars that we care about. And these are basically, this CS would be the union of all these descent directions. Okay, so anything in CS is a descent direction for one of these thetas of interest. And so if it happens that that direction is also feasible, then I can't recover that particular theta star uniquely. So it will violate my like, let's say, criterion. Okay, so this is the set of interests, so the union of these. And the whole point is that this set is, in fact, turns out to be exactly this set. So, and then the proof is complete if we can show that. So basically the CS you can show is the union of all these tangent cones for theta star supported in S. Okay? Clarifies a lot. Okay, good. I don't know what clarifies a lot, but one of these statements clarified. Okay. So why this is the case, let me show you by just some example, and then you can. So the proof is complete if we can show that this CS is, in fact, that cone that we had in the statement of the result. So what we have here is, this is the L1 ball, right? And what I would have is, let's say I have S is equal to 2 here, okay? So we have two possible theta stars on the L1 ball. So let's say I'm looking at only theta stars that are on the unit ball, for example. You can later argue for yourself that doesn't change anything. So let's say if I'm looking at the L1 ball, there are only 2 points here. So only these 2 points that have that support. So there's this sorry, what am I doing? So yeah, so this is theta star 1 is, oh, sorry, this is not, something doesn't quite work here. Right, so okay, so this is theta star 1, this is theta star 2. And they have support, which is just a set 2. Okay, these are, let's say these are the only points at the boundary of L1 ball. So anything on this line is, or anything here basically is like that. But let's look at the points at the boundary of L1. So there are these only 2 points that have support S equal to 2. And now, so what will be tangent cone at this point? the tangent cone are all the directions on which I can descend. So this direction works because when I go in, the L1 norm is reduced because I'm moving into the ball of radius 1. So anything in this ball has L1 norm less than 1, right? Anything outside has L1 norm bigger than 1. Okay, so I can move in this direction, but not in this direction. So if I move in this direction, I'm gonna increase the L1 norm. Okay, so you can see the set of descent directions to the L1 ball are all the things as I move inside the L1. So if you just do this a little bit argument for yourself, you can see that the tangent cone would be just this. Any direction in this sort of cone would be. So it would be basically cone generated by these two vectors. Okay, so that would be the tangent cone. And then similarly, the tangent cone at the other point is again in this guy. So anything that points inside the L1 ball. And then if you take the union, so you have to think about the directions as the origin is centered at theta star. And so if I want to sort of look at them properly, I have to center this cone at origin. So this would be, if I want to look at the tangent cone is basically this guy translated to the origin. So this thing, just move it to the origin, it would be this thing. Okay, that's that thing, right? And the other thing would be this guy, I have to move it to the origin. So that would be this guy here. Okay, so that would be my union of these two. And you can see that the union of these two matches this guy that we had here. Right, so that's basically what we had. This is C2. Right, and you can see why these 2 points are important. It doesn't matter. So I could have taken something here, and the actually I couldn't have done that. The descent cone in this case would be inside the interior. The descent cone would be the entire plane. So argue for yourself why we don't do that. But that's the basic geometric idea. Okay, so right. Okay, does that make sense? Yeah, I could have just the L1. So you have to look at the right. So the fact that this is unit L1 doesn't matter. You could have done it with like smaller L1. Okay, so I'm assuming that the L1 norm of theta star is 1, but that's without loss of generality. You still have to be at the boundary. You can't be inside the ball. But does that make sense to people? Was that a useful attempt at explaining why the union of these tangent cones is that set? Let's see if I have a like formal proof. We're out of time, but let me very quickly. You can also formally prove it. So it's enough to show that this is this set is equal to that set. So delta would be in so I'm using this notation. That's the tangent cone to L1, I believe. So that would be equal to, okay, so T1 is a subset of this where T is equal to 1. Okay, so without loss of generality, you have to argue that I can just look at all the deltas that are, because this is a cone, I can just look at all the deltas that satisfies this inequality with T equal to 1. because I just care about the direction, if there is a different t, I can always rescale delta such that that t is 1. And so I just worry about those delta. And once I have those deltas, then all the other ones can be obtained by rescaling. So let's work with this T1, which is just the, so this is basically, this are all descent directions that satisfy that descent inequality by, with T equal to 1. So that's these things. So I'm looking at the set of all these things. And the main idea is that I can write this part. I can break it into the part which is on the support of theta star plus the part which is off the support as complement. But then, sorry for the rush, but this is 0, okay? 0. So this is 0 because that's the support. So what I end up getting is this is equal to this plus the L1 norm of this guy, and then you rearrange. If you rearrange, you get this inequality. Okay, so delta is in this tangent cone if and only if that holds, and then what you can do is I can take the so this side, this direction is sort of fixed. So this side doesn't depend on theta star. This side depends on theta star. I can take the the supreme over this side. So if so delta would be in one of these tangent cones if and only if this is less than or equal to the supremum. Because if it's less than or equal to the supremum, then it means that there is a theta star such that this inequality holds for that, and it means that its delta would be in the tangent cone of that delta star. So just verify that delta star would be in the union of these if and only if I take the supremum on the other side. And if you take the supremum on the other side, this turns out to be the L1 norm of the delta S. Why is that? Because anyone knows why that is? Because this is always going to be less than, by triangle equality, this is always less than this. And then you can achieve the inequality, let's say, by choosing theta star properly. Need not be 0. You can choose delta theta star such that that triangle inequality holds. And just verify that for yourself. You can take non-zero theta stars S such that the inequality is true. So we get this inequality. So delta would be in the union if and only if this part is less than or equal to this, which is just the definition of the cone. So this part was a little bit rushed. Let me know. I mean, if you have questions, if you look at this and you have questions, you can ask me next time at the start, or just now if you want. Questions?
In linear programming, electrical engineering 36A, I looked in my notes and I found the slides where we did a really similar proof with something called the null space condition, which I'm having a little trouble seeing how it's equivalent to this condition. I don't know.
Okay. Maybe you can post that on Campus Wire, and then we can chat there.
Okay.
Post that condition there.
Sure. Okay.
And then people maybe can compare it with this and see if it's the same or not. Okay. Or you can tell me what it is if you can. Or
trying to like drop the file into here. I don't think you can do that in Zoom, but I can, I guess, share my screen. Oh no,
let me see if I have the.
But I can Campus Wire right now, and then
sorry.
I'll post it on Campus Wire now, and then link to it.
Right. Okay, that sounds good. That would be nice. Any other questions? Okay, we can come back to this. I'm gonna I think I have this posted this slide, so I'm gonna update them, and you can take a look. And also on campus where you can ask questions, or next time. It's an interesting proof. Just take a look at this yourself, and if things are not clear, I can go over them again next time. Okay, thank you guys. I think sorry that we went over time a little bit, and see you guys next week hopefully. Okay.
Thank you very
Bye bye.
much.
Thank you.
Bye-bye.
Thank you.
No problem.